Today I will say what is a morphism. So I'll take A algebraic variety over K, and I'd say what is a morphism to beer X. So this is maybe not an algebraic variety, but at least we can define the morphism, and this is given by A goes to FA, where this is, you take a birational map like this, so you have an isomorphism between two which is compatible with A. So you have a birational map, so for any point A you get a birational map. This is surjective. So for any point A, you have an open subset where this is defined, which is not empty by this assumption. So, and you get a birational map of X. So this is like a continuous way to define a map, or algebraic way to have a family of transformations. And now we can ask what is an algebraic subgroup of the group beer X. So what is an algebraic subgroup of beer X? So maybe I can try to. It's not possible to. Okay, it's not possible to have the two together. Okay. So there is one way, classical way to see this. So we take G, an algebraic group, define over K, and we can define what is either an action of G on X. Well, in a biregular action, it's classical, and you can do the same for a rational action. So you have a rational action. So this means that this is a rational map, and you want to satisfy the axiom of action, and this implies that you get some for each element G, you get a birational map from X to X. So in another way, you can also say that you have a morphism with the definition above, a morphism like this, which is also a group homomorphism. So this is just another way to explain the classical way. So this is one way. You take one algebraic group and you explain what is the action, and then you can say that dG is a subgroup, an algebraic subgroup of the group of birational transformation if this is injective, so if the kernel, in fact the schematic kernel in characteristic P, you need to look at you want it really to be trivial. So basically you want that this is injective, but you want maybe to check it properly in characteristic P, so this is why you need to look at the kernel really. Schematic kernel has to be trivial, but anyway, this is. Pardon?
Is it clear that the kernel is a closed subgroup?
It's yes, it's not so clear, but yes, it's true. Yeah. You have to explain what is the kernel and write it correctly. Take care. Okay. Yeah,
it's a homomorphism of abstract groups. So
yeah, if you look in characteristic 0, you just look at the homomorphism. You want it to be injective. But characteristic P, if you just look at the close point, you have some troubles. So anyway, I will not go too much into these details. It's not really what I'm interested in to yet, but you see we have still some little troubles. And what I don't like in this
So for example, if suppose you're thinking about it, suppose your group scheme, you were inherited P,
yeah.
and your group scheme were infinitesimal, like killed by Frobenius, but maybe highly non-computed, right? And the map was kind of 0 at the level of the tangent space, then would it have to be 0 at the level of, so for group schemes, right, if you have a homomorphism inherited P, whose kernel is filled by Frobenius, if it vanishes on the tangent space, it is the trivial map of group schemes.
Yeah.
This is kind of equivalent to like Peely algebras, and so in this setting, that would be a kind of like test case for this notion, right? If you have the map, and it's 0 at the level of the kind of tangent space, the dual numbers kind of stuff.
Yes.
Is it actually the zero trivial action? I'm saying connection with some of these questions.
Yeah, I think so. In fact, if you have a rational action, you can conjugate and get a regular action. So afterwards, the rationality is not a big problem. Sorry, I destroyed this. So I think it works, but I didn't check all this.
Wait, are you saying that the use of birational for x as opposed to odd x is no difference?
If you change the x, you can assume that it is biregular, but you have to change the x. You have to change by a birational map, which is the proof is a proof of Weyl, a classical proof, but which is not so easy to read. So it would be good to have a modern reference, but it's really at least so you can change, and then having rational, it's not so the big problem here. It's really okay. I hope what is my problem? Not really a problem, but when I look at this, is that for me, you take an algebraic group here, which is outside of your beer X, and then you try to make an action, and so you get something here, but the structure is here and not really inside. So I try to give some intrinsic way of looking at it. So not so intrinsic as you will see, but a bit more. So we like a more intrinsic definition. So I will give another one and try to see that it's the same. So we consider the Zariski topology on beer X. So this is what I explained yesterday. So it's something is closed here if and only if when I take it back by any morphism it's closed. So in some sense it's again not really intrinsic because I used the other definition. But anyway, so F is closed if and only if the preimage is closed for any rho on beer X morphism. So you get some topology, as I explained yesterday. It's with this topology on beer X and on beer X cross beer X, the multiplication is continuous, the inverse is continuous, and if you change the X by something birational, it doesn't change it gives you a homeomorphism on the beer X, which is so it's some natural topology which is independent of the birational model. So this is a good thing. And now I say that G in beer X is an algebraic subgroup. So this is my definition. It's another definition. If and only if G is closed for this topology, and of bounded degree. So what does it mean, bounded degree? So if I have a map, the rational map from X to X, I can see it as if X is a projective, I look it at X in Pn. I have F birational map, so it's given locally, but by something which is a rational function, so it extends to something which is rational here. There are many ways to extend it because locally you have to change. So you take the minimal way and you define it the degree like this, for example. There are many different degrees that you can explain, but this is one way to say. And bounded degree, you want that this is bounded for all your elements of your group. And this is, it seems very dependent of the embedding, but having bounded degree, it's not the degree itself. It's dependent, but when you do conjugation, you just you have inequalities both sides. So if it's bounded after, it's bounded before. So bounded degree is something which is really intrinsic, and so you can say closed and bounded degree. So a priori, I just say algebraic subgroup is this. And then I will try to see that it is the same as the other one. At least for X is Pn, I will explain you that it's the same. And so if you have a subgroup which is closed and of bounded degree in beer, I can find algebraic group structure on it, which is unique and which satisfies which has good properties. So that, for example, this morphism, a priori, we have a family of morphism. We don't know if it corresponds to a functor. We don't know if it's representable. For yesterday, I explained it. In general, it's not. But if you take algebraic subgroup, it is representable. So I will explain that in this case it works. Okay. So the theorem I will explain today. It's again with Jean-Philippe Furter. The same as the article as I explained yesterday, which appeared in 2013. So I take, let G be a Pn, a subgroup closed subgroup of bounded degree. Then you have there exists a unique algebraic group structure. So it's already a group, so I just put some structure of algebraic variety so that this is, if you want, there is an algebraic group, so in a homeomorphism between the two on G, compatible with the product, and such that morphisms A to be Pn having image in G correspond to morphism of algebraic varieties. So in this case, if you take morphism having image in this subset, then it is the functor is representable. So we can do, in fact, definition of some subset in beer Pn is like a subvariety if this morphism corresponds really to a morphism to a variety, and this is the case for this. So for a subgroup which is of bounded degree, it works. If you remove the subgroup, just the bounded degree, it doesn't work, as we explained yesterday. And if you have something of fixed degree, so always the same degree, it works also, as I explained yesterday. So here the degree is of course not fixed because you have the identity which has degree 1 and most of the elements have no degree 1, except for automorphism of Pn. And but it works. And secondly, if you take take an algebraic group over K and A to beer Pn, like before, I wanted a morphism and a group morphism. Then the image is the image G is a closed subgroup of bounded degree, so it's like before. So it has a unique structure like this, and so correspond to a morphism of algebraic groups. So this shows that the two definitions are the same, and so you can also define, like you define what is a morphism like this, and you just look at the image. So maybe the structure on the image is not the structure that you took, because you have morphisms which are surjective but not isomorphism. But at least there is a structure which is unique, which is like the minimal one.
Presumably very few elements in this group of birational transformations
Mm-hmm.
can be fit into a group of elements of bounded degree. Right? If you take powers, the degree will, in most cases, the degree will increase.
If you take an element of pure Pn, general element, it's not contained in a algebraic group here. In fact, we can say that I will make some remark. So the first thing is that if you take f in bir Pn, some people say that f is algebraic if and only if the degree of Fn is bounded. So you can say in n or z it's the same. If one is bounded, the other one is bounded. And so some people write it like this, like a definition. They don't, but in fact, algebraic here in this sense, it's by this statement is that it's contained in an algebraic group. And yeah, most of the elements are not like this. You can in fact study what is the, in general this goes to infinity, and you can study what is the growth of this. So in dimension 2, for example, we know that the growth is either linear, quadratic, or exponential. And if it's exponential, you can compute what is the dynamical degree, which is it corresponds to lambda to the power n, and the lambda we can say a lot of things on this. So it's a Piso number, a Salem number, and there are lot of result on this in the dynamics, and it corresponds to the log of the entropy. So there are many things on this, but in dimension 3, for example, we don't know. We can do linear, quadratic of the degree 3 also, but we don't know if we can degree 4. We don't know if we can do something between polynomial and exponential in general. We don't know also if we can have something, for example, which is below of linear, for example, very slow. Or there are many questions that we don't know, and which correspond. If we can understand this kind of sequence, we can maybe understand if there are, for example, some groups which do not embed in bir Pn for large n, for example. And this is not, or in the union of the bir Pn. For the moment, there is no answer to this. Okay, so this was a digression on this. And the second remark, which is in fact due to Michel Brion. So I discussed with him when we were writing this article. So one can show that in this case, in Pn, that G is linear. So every algebraic subgroup of the Cremona group is always linear. So the proof is like this. So you have G acting on Pn, and as I explained, you can change the model. So this is the result of while. So you have to believe me, and even you have to look at the proof. It's quite. So you can change the model so that you act on a projective variety regularly, and then you look at the map from X to AX, the Albanese morphism, and by the result of Nishi-Matsumura, you have the action of G on this factorized on this Albanese factorized to AG AX. So you can. I found the proof in an article of Michel, and then in this case, AX is because X is rational, AX is trivial, so AG is trivial, and so G is rational. It's not correct?
You don't need to use this theorem of fact. You can work directly with by rational action.
Okay.
It means a true action of the variety of G on the one.
Okay.
This paper of Matsumura is one of the papers of the early 60s, which is written in the old language, very hard to understand now.
Okay, that's why I look at the proof in your article. So the same. You take the Albanese for G, and because this is trivial. So this is trivial. So the Albanese morphism of G is trivial. So as Michel explained, it means that G is linear. So when yeah. So because X is rational, you cannot have an elliptic curve, for example, which acts rationally on Pn. Okay, so I will explain. My aim is to explain a bit the proof of this. So, how do you do this kind of thing? So, in fact, we think that this could be maybe true for if you replace Pn by any x, and we are trying to work on this. But there is one thing in the proof that we need is that you need a bound on the degree of the inverse. It's not. So for Pn, it's an easy statement and very classical, but it's not the hard part. But in general, it's not so clear. So there is a proof of the fact that there is a bound for the inverse, which is recent by Bogomolov and von Bontner and Bönig. But yeah, I don't understand the proof. So, and there is a bound is explicit and it's too low. If you, for some number, it gives you the degree smaller than 1/2, for example. So this is not possible. So I think there are still some troubles if you want to generalize this to any variety, but I hope it's possible. But at least for Pn, we can do it. So I explained it like I did yesterday, that I fix the n, and for any degree, I take the polynomials of degree d, homogeneous polynomial of degree d, up to equivalence f0 is equivalent to lambda fn, lambda in k star. So this is a projective space. And inside I take the map which are birational. In fact, the polynomials which correspond to a birational map. Is birational. And so this is locally closed. As I said yesterday, the dominant, if it's dominant, it corresponds to an open condition. It means that the Jacobian is not zero. And then when you have the dominant, the birational map are closed in the dominant ones. Okay, and so this is an algebraic variety, and then you have the map pi d to BRPN, which correspond, you take an element and you take as a birational map, and this is you get all maps of degree at most d. So not of degree d, because you can have some common factor, but you get all maps of degree smaller or equal than d. And this is if you take the map which are exactly degree d, but this is one-to-one, but in fact it's better, it's a homeomorphism. This is a subset of the birational transformation, so you have the topology which is given by these families, and this is an algebraic variety. And in fact you have an homomorphism because you have every family which lends to something of fixed degree correspond to a map to this set. Because here you have no problem of multiplication, so you can find that it's unique, and you write in local coordinates and you check just that it's the case. So you have a homomorphism. So on the part of degree d, it's the same, and part of degree lower, you take a point. The preimage is then the preimage. You can see that it's a projective space. It depends on the degree. When the degree is smaller, you can multiply by a polynomial, so these are bigger and bigger. It corresponds to the set of polynomial of degree, the difference. So in fact, the preimage of a point is not on, it's a projective space, so it's closed in this, and you can find that the pi d is closed. So this is continuous pi d, and this is moreover closed. Okay, so this is some tools that we need. Now I will explain the lemma, which is the key point for the theorem. So I take a subgroup, closed, connected, for the Zariski topology that I define, and of bounded degree. So what I say, I take D is the maximal of the degree of F in G. So I take the elements of highest degree, and I take pi d minus 1 of G. I take all maps of degree maximal, And so it has degree at most D, so the part of degree D is open because the map of degree smaller than D is a closed subset. And so this is a big part of the group. And I take this one, and then I take it back, and I take the closure. And I write, okay. So why do we do this? Is that if you take pi d minus 1 of G, this is not good because the preimage of this part, okay, it's bijective, it's a homeomorphism, but on the part of degree smaller, you have many people. So it will have, if you take pi d, so this is contained in pi d minus 1 of G. So this has many irreducible components. And I will show that this one is the good one, and this one is bijective to K, to G. So then gives a bijection. K to J. In fact, it's a homeomorphism. Morphism A to G having image in G corresponds to morphism of algebraic varieties. So you have something which is in Pn, in BPN, so this is that's just a topology, it's not an algebraic variety. And I take some part, I take it back here. This is now an algebraic variety because it's, I will explain, it's a closure of something which is locally closed there. And so now you have an algebraic variety and you want to say that this is the good structure. So this explains that you have the morphism, which a priori are just morphism by definition, correspond to morphism of algebraic varieties. And the last part is that the liftings to K, because this is a bijection, so you can of the multiplication and inverse are morphism of algebraic varieties. And so when you have done this, this will give you at least the first part. And the second part is not so hard, follows almost from the first one. So in fact, this explains how you construct the structure. You don't take the pullback directly in pi d because it's too big, so you take the part of degree d and you take the closure. And you get, you will see that for maps of degree smaller, because you have, when d is 1, but everything is trivial, but when d is 2 or more, you have elements of degree 1 here because you have the identity, for example. And so you have some way to, you have many possibilities for the pullback of the identity, and this process gives you the good one. Okay, so I will prove the lemma. At least explain the idea. And in fact, this lemma, which is something positive for the algebraic groups, as I explained for the group itself, it is something negative, you have no good structure. This lemma was useful afterwards to put the Euclidean topology on this one, for answering the question of Serre on the Euclidean topology on BRPN. Okay, so the proof of the lemma. So first, you show that G is irreducible. So a priori, you have just something connected. I explained that this follows from this, but if it's connected, but if it's not connected, you have finitely many components. You can prove this, and so the connected case is the interesting case. But you have to first to show that it's irreducible, which is true for the algebraic groups. But in general, here we don't know that it's an algebraic group. So what you do, you take pi d minus 1 of G. So this is G is closed, so the pullback is closed, so it's a closed subvariety of HD, and so you write it as a union of irreducible components, and then you apply pi d, and so you get G, which is the image of all these people, and the image of something irreducible is irreducible, so you get union of irreducible components, and maybe some are contained in the other, so I take the maximal ones. Okay, so this is first decomposition, and then I do a classical thing. I call the elements for each I the element in G, so that G Z1 is contained in Zi. And this set is the same because you have irreducible subset which are not, no one is contained in the other one. Is the same as to say that G Z1 is equal, so is contained, is the same. And now you can write it as an intersection, so it's intersection of H in G, so A Z I Z1, sorry. So like this, you see that it's closed. And so each element, it sends, when you multiply Zi, then one, you get one of the other components. And so, because the multiplication is continuous, I didn't explain, but you just, for the moment, we just have something, multiplication is continuous, and some topology, which is, we don't know what it is, but at least it's not algebraic group, but it's not so far. And so you send one onto another one, so you have a disjoint union of A1 with AM. So it's the disjoint union of closed subset. So each one is closed and each one is closed and open. And because J is connected, then G is AI. Okay, so G times Z1 is equal to Zi, but this is G. So M is 1. So you have only one component. So this is, well, this is a, oh, I don't know, this is no blackboard. Sorry. This is probably, the same as what we normally do for algebraic groups. Here we don't know that's algebraic group, but there are many things which work the same. Okay, so this was the easy part. You show that it's irreducible, but what is good now is that you have you can use this to show that you want pi d of k is j. So you have taken back the part of degree d, and then you take the closure. I want to show that you get all M elements, not only the elements of degree d, but also the elements of degree smaller. So G is irreducible. So G, D, I will call it the new intersection of P Pn of degree d. So I take the elements of degree d. This is open and dense. In G. So this is the good point. And then I take it back. I have Kd this I call it Kd definition. And now I have this is the part of the greedy. So as I explained before, you have this is a Homeo. So Kd is irreducible, and so K, which is Kd bar. By definition, I created this is my Kd. So it is irreducible. Okay, and now K is contained in PD minus 1 of G. So PD of G, because PD is so this is so this is contained, but that I want just to write that it's equal. But as I explained, pi d is closed. So okay, but it contains this. Because I take it back, I take so I use the fact that G is irreducible. So I have some map, some subset. I have enlarged it. I get everything when I take it back. So this is the good point. At least for any map of degree smaller than D, I get one element at least. What I want to show is that I don't get at least one, I get exactly one. So okay. And now comes the part where we need to do a bit something about this group, because for the moment we did nothing about this. So I will take. I want to say that for every f in G, I take an element. I correspond to the. I want the multiplication by f, and I want to say that this corresponds to morphism. Of algebraic varieties K to K, which is compatible with. I know that this is surjective. This is the map G goes to GF or FG. Yeah, GF. So I want to lift the multiplication by at the right by some elements, and I want to show that this is correspond to a morphism. So this starts to explain the structure of multiplication, but it's not only this, because it's important because we have a good structure on the map of degree D. So if I can multiply, I have a good structure everywhere. So that's in fact isomorphism. I will show afterwards that it's an isomorphism. Okay. So if I want to multiply by f, gives a morphism. My element. Sorry, my element is. Sorry, my element is in K. This is the multiplication by the image of f. So I take an element upstairs. Okay, and now I multiply by f, gives a morphism from hd to hd square, which is just I take an element g and I do formally the composition. So here I have an n tuple of polynomials. I just replace inside. I had something of degree d, now I get something of degree d square. Maybe it has a lot of common factor. In fact, I know that it has a lot of common factor because I know that the image stays in the group. So there exists some simplification. Okay, so we claim that we can simplify the image by a polynomial p of degree d square minus d, because I have something of degree d square, I want to go to degree d, but which is, so this is clear for every g, but which is the same for all d. For all g. So I want to do it globally. And if it's the case, afterwards I just simplify, I go to hd, which is not so far from this, and then I show that it's in k. Okay. So a bit of bar rational geometry, little bit, will come. So we know that this is possible. Always for every g there exists a polynomial, and so g is divisible. Ah yes, okay. First, so we only need to show this on an open subset, because my k is irreducible. I just need an open subset when I will take degree of g, in fact of pi d of g is d g. A priori, I know that there is a simplification, but I take the slowest one, not the slowest one, the smallest one. So I assume that the map is of degree d, and the multiplication also. It gives you two open subsets, intersect, I get an open subset. It's good because this is of course something close to have this. So if it's okay on an open subset, it's okay everywhere. So I do this, and what is good with this is that now there exists, because a polynomial pg of degree d square minus d, which divides g. It was of degree d square. I know that it is of degree exactly d, because if it was smaller, maybe I couldn't. It would be something of degree d square minus d plus 1, for example. It would be problematic. So I know that there exists only one polynomial, in fact unique up to multiple by a constant, which divides this. Okay, and now what does it mean geometrically? If you look at the polynomial pg equal to 0, you look at this in Pn. You apply first f and then g, and you have something which simplifies because it becomes 0 when you replace. So it means that all these guys, when this is equal to 0, they are sent onto the composition of two elements is not defined in some sense, which means that the hypersurface is sent on the base points, is sent by F on the base points, so the points where it's not defined of G. So F contracts this hypersurface. So because it contracts the hypersurface, it means that PG divides the Jacobian of F. Jacobian is just I take the polynomials, I take the partial derivative, and yeah, it is contracted, so that means that it is 0 on all the set, so it divides. Okay, so this is good because I have one element. I have only finitely many polynomials which divide this. It's fixed, so I get finitely many possibilities for PG. And so you write your set as a union of finitely many set, and because it's irreducible, you can find that there is only one. And so you get this polynomial. So, and then what you get, you can simplify. So this polynomial is the same for everybody. So you go to HD square, you compose, and then you go to HD by dividing. In some set, I divide by the polynomial. It's something algebraic, and then because I know that this is the composition of the map, I know that where I obtain it's not only in HD that I land, I land in K. In fact, I land in PD of -1 of G in K in HD. But you take the part which is of the highest degree and it intersects the other one, you take the closure. You show that it is really in K, in fact. So we have the C. So we get this map, and now using this, it's good because you can multiply. And so on the, yes, you can multiply by mu F. So you have a morphism like this, and then you do for mu F minus 1, so you get isomorphism. Because if you compose mu F by mu F minus 1, you know that on the part which is of highest degree, it's the identity. So it's the identity on an open subset, so it's the identity. And so you get an isomorphism, so you have left the multiplication by an isomorphism. And so you can show that my lemma, you have a bijection, because on the part of degree D it's a bijection, and then I multiply to get on an open subset around everywhere, everybody, and I get a bijection. So I obtain some algebraic variety with a bijection like this. And then to find the morphism here, if I have a morphism from A which has the image here, I take the part of degree D, and now I have on the part of degree D I have only one way to lift, so it's no problem, and then I use the multiplication again, and I find that I have again only one way to do this, and everything works well. So there are something to check, but it works. And the liftings with the multiplication by the right works well. It was what I explained. And so you can do it for the morphism in general, so you can just again use what I explained. So I will not do this into the details. And so you get all this. So you start from something in pure Pn, you lift it, you get a good structure of algebraic variety, and in fact of algebraic group, you get the morphism and the inverse, which are given. And if you do the second part, you start from an algebraic group, you take the image. So I will explain the second part. So the lemma gives the first part, yeah, at least for the connected case, but once you know, you show as usually, like in the algebraic group setting, that you have a finitely many components, because it's you take it back, you have an algebraic variety. Then everything works well if you know what happens on the connected components. It's just So the first part follows from the lemma. And the second part, it's the easy part. So you take this in beer Pn. This is an algebraic group. So you can show that it's of bounded degree just because it's given by a morphism in my definition. So you have no choice. The map from A cross Pn to A cross Pn, it's given by some degree, so you have bounded degree. And so the image is of bounded degree. You assume that it's a morphism and a group morphism, so the image is a group G of bounded degree. So G bar, I don't know if it's closed, so G bar is an algebraic group by 1. I lift it and then I use all the theory in algebraic groups. If you have a morphism from an algebraic group to an algebraic group, the image is closed. And so in fact I have image is closed. And now I had a morphism to G bar, which leads to a morphism of algebraic group. Image is closed, so G equal to G bar, so the image is closed, and it's an algebraic group. And so I get this, and so I have the result of the theorem. Thank you.
Any questions?
It looks, I mean, for Pn, you have really nice theorem. You think this could generalize to other graded setting like toric variety to replace Pn?
Yes. In fact, I wanted to do in general for any projective variety. So for this, we started to introduce the WD. In fact, you put it in a projective space, and then you make homogeneous polynomials up to the equations. So this is good. It's again a projective space. And then you compute the HD. But there, the HD, you want to show that it's locally closed. For the proof, we need to have a bound on the inverse. So already now you have a little problem. But maybe there's some way to cheat, because you could explain that the degree is not the extension as a rational map, but as a birational map. And this is always possible if you take at least the codimension 2. And now the inverse of the bound of the degree, we know it because we know it for Pn. But it's maybe not the good way to do. But that's the first problem, to show that it's locally closed. And afterwards, we can try to imitate this to make the lift and so on. And yeah, I don't know, maybe there are some troubles. Maybe if you take some toric varieties, will be easier. And we didn't go enough far so to see all the troubles which could appear. But I would like to have the same result for any algebraic variety.
Is there anything known about maximal algebraic sample? That's not a proper question. Okay, if you have an algebraic sample of here Pn,
Mm-hmm.
you cannot bound the Unit radical because you have these examples
Yeah.
with A2 with a large part. Can you bound the dimension of the reductive part of the code?
Yes. So the torus is of dimension n at most,
Sure.
and afterwards, but there, even just the torus itself, it's a complicated story, because on dimension up to dimension 3, I think it's okay. So all the torus are conjugate to the standard one. But if you go to dimension higher, there are examples in dimension 6 of torus of dimension 3, which is maximal. So it's quite complicated. It's an example of Popov of a torus of dimension 3 in beer P6, which is maximal. So it means you have some torus which are embedded strange way. So these are the story which is already for the algebraic, just the torus, it just already complicates things. And afterward, in general, for example, in dimension 2, we know that any algebraic group is contained in a maximal algebraic group. And then you can look at But the proof of this, it's just by classification. So dimension higher, I don't know. Maybe you could have an infinite union of algebraic subgroup and
What did you get an example is xy goes to x and y plus a polynomial in x?
yes. So for automorphism of an, it's false. You can have really the union, but for yeah, exactly. For if you take this is a good example. If you take y plus polynomial in x, degree of p is bounded by n. So you have a union of yeah, that's true. You could have a infinite sequence of algebraic subgroup one containing the other one, but each one is contained in a maximal one. And the maximal here in this case, in the group of birational transformation, is the automorphism of the Hirsebert surface of degree n. And so you have some quotients which comes, and now it becomes maximal. So you can try to catch the polynomials by putting some quotients, and now it's maximal. But it's true that yeah, if you take first you have an infinite sequence of algebraic groups one contained in the other. That's not a problem. But you could have that no one is contained in a maximal one, and in dimension 3 or more. In dimension 2, no. For beer, everyone is contained in a maximal one. So yeah, we don't know the maximal. And there are some even in dimension 2, you have some maximal algebraic subgroup of order 2. So you have some which are of dimension 1, 2, but you have also some which are finite. So it's like a very rigid story.
So, if there are no other questions, let's thank once again.